The overall goal of this procedure is to assemble a bench-scale photosynthetic bioreactor with continuous light, pH, and temperature monitoring for algal growth experiments.
So quantifying algal growth using a monitored and controlled setup allows researchers to better assess algal growth, which can help answer key questions in making algal-based biofuels a reality.
The main advantage of this approach is that it is a customizable and potentially more affordable setup for monitoring algal growth experiments in real time.
We wanted to develop this type of photosynthetic bioreactor when we realized the importance of maintaining control within the algae's dynamic culturing environment.
Visual demonstration of this method is critical, as many of the steps are difficult to learn if you are not familiar with electrical engineering terminology and practices.
To begin this procedure, construct a bench-scale PBR. Determine the size, shape, and design of the PBR body and lid as described in the text protocol. Using the transmitter wire, connect the unity gain amplifier to the pH probe. Then, pick up the coaxial adapter that has positive and negative port terminals. Connect the adapter to the other end of the unity gain amplifier. To make a low-pass filter, use wire strippers to cut two 15-centimeter pieces of green connector wire and one 30-centimeter piece of black connector wire. Strip approximately 0.6 centimeters of insulation from one end of each of the green wires and from both ends of the black wire. Next, strip approximately 1.25 centimeters from the other end of the green wires. Carefully wrap one leg of the 1000 ohm resistor around the 1.25 centimeter strip section of one of the green connector wires. Wrap the other resistor leg around the 1.25 centimeter strip section of the other green wire. Using a soldering iron and lead-free solder, solder the resistor legs to the wire. Let the solder cool for 2 to 5 minutes. After this, cover the resistor and soldered wire with a 4 centimeter piece of heat shrink tubing. Using a heat gun, heat shrink the tubing, making sure that the plastic wraps tightly around the resistor and wires. Next, secure one end of the black connector wire to the coaxial adapter's negative terminal post. Insert the other end of the wire into one of the data acquisition and control unit's ground terminals. Connect one end of the green connector wire to the coaxial adapter's positive terminal post. Then, insert the other end into a free analog input terminal on the data acquisition and control unit. Insert the positive lead of the 1000 microfarad capacitor into the same analog input terminal. Secure the capacitor's negative lead to the same ground terminal used for the black connector wire. After this, connect the temperature sensor to the data acquisition and control unit as outlined in the text protocol. After setting up the live data acquisition and experimental file, insert both the pH electrode and the temperature probe into pH calibration buffer 7. Confirm that the solution is at the desired temperature as outlined in the text protocol. After the pH electrode voltage output has stabilized, log both the temperature and the pH electrical data to a file. Make sure no conversions are applied to the pH channel and channel averaging is turned off. Repeat the calibration for buffers 4 and 10. Generate a conversion equation as outlined in the text protocol, and update this equation in the experimental file. Next, apply this pH conversion to the pH channel. After preparing the algae inoculum and growth medium, set up the PBR in preparation for the experiment. Thread the light sensor wire through the lid port. Then, mount the light sensor head onto the PBR lid extension mount. Then, use a rubber stopper to seal the lid port closed. Place the impeller shaft over the DC mini gear motor shaft inside the PBR lid, and secure the shaft with a set screw and an Allen wrench. Add the prepared algae-specific growth medium. After this, place the lid on the PBR and secure it with screws. Place in an incubator at 25 degrees Celsius. Insert the temperature probe into its designated port, securing it with a rubber stopper. Next, secure the pH probe in the reactor lid's PG 13.5 threaded mount. Ensure that the light sensor is connected to the data acquisition and control unit with a low-pass filter as described in the text protocol. Then, power on the mixer impeller to the desired speed. Set up the variable DC power supply next to the PBR. Turn on the power supply and adjust the voltage until the voltage value reads 0 volts. After this, turn off the power supply. Connect the impeller motor power lines to the positive and negative output terminals of the variable power supply. Turn on the power supply and slowly increase the voltage until the desired mixing speed is reached. Next, center the grow lamp along the front face of the PBR, making sure that the light path is oriented towards the light sensor. Turn on the grow lamp and adjust the light intensity as needed by moving the lamp toward or away from the reactor. Monitor and log the sensor data for 6 to 24 hours as outlined in the text protocol. After this, use a transfer pipette to add algae inoculum through the sampling port. After monitoring the conditions to ensure they stay within range, use a pipette to remove the cultures for analysis as needed through the sampling port. Using the data display, monitor the water temperature. Manually adjust the incubator air temperature set point to keep water temperature constant.
pH is controlled with a 12-volt solenoid valve in line with a 99% CO2 tank. The valve is open via the data acquisition and control unit.
In this study, a photosynthetic bioreactor is constructed to monitor and control bench-scale algal kinetic growth experiments. The log temperature data demonstrates how the light illumination, incubator air temperature, and energy dissipation associated with algal growth can change the temperature within the bioreactor. This real-time data is used to adjust the incubator controls, as needed, to control the dynamic culturing environment. The measured light further emphasizes the dynamic nature of this growing environment. While the light sensor reading is approximately 100 ppfd before algae, it immediately drops to 85 after the reactor is inoculated. The light continues to drop, reaching less than 5 ppfd on day 7. The decrease in light intensity may be due to the increase in biomass and cell count, or to the increase in absorption due to increased chlorophyll content. In either scenario, this shows that the algae are still active through day 7, despite low light levels. The continuously logged data shows that overall, the pH is adequately controlled using the implemented control algorithm. While there is an expected pH increase immediately after inoculating the PBR with algae, it is quickly controlled by the system. However, the live data does highlight how sensitive pH electrodes are to external electrical noise, which can lead to extreme outliers and potentially disrupt the control systems.
Though this method is implemented for an algal PBR, these live monitoring techniques can also be applied to other microbial reactors that require pH and/or temperature monitoring.
Once the PBR is constructed and the data acquisition is complete, one should be able to set out a PBR for live monitoring for experiment in 1 to 2 hours.
While attempting this procedure, it's important to remember to read and understand the measuring principles behind how your sensors operate, and to validate your measurements with other handheld devices.
So following this procedure, other enhancements like automated pH control can be added to your PBR setup. These instructions provide a foundation for the data acquisition framework required before implementing these more sophisticated control feedbacks.
Don't forget that working with electricity, soldering iron, and acrylic cement could be extremely dangerous, so precautions should always be taken.
After watching this video, you should be able to assemble and set up a bench scale PBR for live pH, temperature, and light monitoring.